Okay, so this is a bit of a digression in the sense that all the molecules I've done so far are molecular compounds in that they will have a covalent bond between the atoms. And so this next one I want to do, which is a bit of a digression, is a Lewis structure for an ionic compound. So the ionic compound we're dealing with here is Na2O. So let me go ahead and write out the Lewis structure and then talk about why this is sort of a bit of a digression, and it probably will not be on your test. Okay, so here, can you calculate the total number of valence electrons in sodium oxide? So sodium has one valence electron, and there are two of them, so there are a total of 2 electrons that are contributed by the 2 sodium atoms. Oxygen has 6 valence electrons, and so there are a total of 8 valence electrons in this structure. And so what we're going to do is we have to deal with 4 pairs. So we have to probably have oxygen atom in this ionic compound to be in the center. And so here I can put a sodium here and say a sodium here, and this is correct. Now let's go ahead and put in the 8 valence electrons. And so 4 pairs, so there's a pair here that goes here, a pair here that goes here. So one of the things you might ask is, how about the other pairs? Can we put other pairs around sodium? So sodium is a little bit unusual. It's in group 1, and all the group 1 elements can be stable with just a pair of electrons. So sodium will not get an octet. You'll learn that for group 2 and group 3 elements. Those elements can be stable without octets, so they can have lower numbers. So here, sodium here will be stable with this pair of electrons, and this sodium will be stable with this pair of electrons. And so we have the other 2 pairs here. And so this is an ionic compound. So this is not quite a correct Lewis structure. When you have an ionic compound, you don't draw lines between the sodiums and the oxygen. You leave them as dots. And a final thing you have to worry about in the Lewis structure for an ionic compound is you have to put charges in the ions, because again, these are not atoms here. Remember, this is ionic compound, so these are ions. So the sodium has a positive charge, and the oxygen has a negative charge of 2 minus. And then finally, the anion, which is the oxygen, gets brackets. So this is the correct Lewis structure for an ionic compound. So I don't think you're going to have to draw a Lewis structure of an ionic compound for your test, because it's a little bit different than the rest of the Lewis structures we're dealing with. But I just wanted to show you, if you have this on your Achieve homework, how you would do that. Okay, so let's move on. Okay, so now they get a little bit more complicated. Okay, so the next molecule is H2CO, which is formaldehyde. And so let's draw some possible skeletal structures of what this could be. So we might have an H here on the terminus, an O here, an H here, and then a carbon up here. So that's a possible skeletal structure. Another possible skeletal structure is having the carbon in the middle and then the oxygen in the periphery. So which skeletal structure is correct? The skeletal structure is correct is both of them have terminal hydrogens, which is good, but there's one skeletal structure that's much better than the other one. The one that's much better is the one where the central atom has less electronegativity than this oxygen here, which has more electronegativity. So this is a good skeletal structure because carbon has a lesser electronegativity than oxygen, and the atom with the lesser electronegativity should go in the center of the structure. So let me erase this one, and then let me rewrite this one. So we have carbon here, oxygen, and then hydrogen, and then hydrogen. Okay, so let's count valence electrons. So oxygen has 6 valence electrons. Carbon here has 4 valence electrons. There are 2 hydrogens here, and so we have 2 hydrogens with 1 valence electron apiece, so a total of 2 electrons contributed by the hydrogens. And so what are the total number of valence electrons here? We have 6 plus 4 is 10 is 12. So we have 12 valence electrons. So we have to deal with 6 pairs. So let's see how we do that. Okay, so we put a pair here between this carbon and hydrogen, a pair here between this carbon and hydrogen, a pair here between the carbon and oxygen. And now let's go ahead and we need 3 more pairs. Okay, so we can put the 4th pair here, the 5th pair here, and we can just put the last pair around oxygen. So what I'm hoping you can sort of see is that this is probably not the best Lewis structure. And the reason is wow, I'm hoping you can sort of see this oxygen here has an octet of electrons. The carbon does not. It only has 6 electrons, and it needs an octet. So do you remember what you do to create an octet for carbon? What you can do is you can take one of these lone pairs and move it into the bond between carbon and oxygen. So let me redraw the structure here. So the hydrogens are fine. And so what we've done is we moved a lone pair from the oxygen into the carbon-oxygen bond. So there are 2 pairs here now. And we have the oxygen here, and we have 2 lone pairs that are left. Okay, now let's do a count of octets. And so you can see that oxygen has an octet, and you can see carbon here also has an octet. And so it looks like those are fine. And then the hydrogens here you can see have duets here. Okay, so the final Lewis structure should be this for formaldehyde. So that should be correct. And you can figure out the polarity of the bonds on your own. So let's move on. Okay, so the next molecule is a little odd. It is the nitronium cation. So its formula is NO2, and it has a positive charge. Okay, so what we're going to do is I'm going to draw a skeletal structure. And so there are a bunch of possibilities, but the correct possibility is with nitrogen in the center because it has less electronegativity than oxygen. Oxygen's on the periphery. So let's do a valence electron count. Nitrogen has 5 electrons. Oxygen has 6 electrons, but there are 2 of them for a total of 12 electrons. So we have totally right now at this point 17 electrons, but here's the thing. Note that this molecule has a positive charge. And so you've already learned that when a molecule has a positive charge, then it's deficient in 1 electron. So because this is positively charged, we have to remove an electron from the count. So really, we have 16 electrons to deal with, which is 8 pairs. Okay, so let's go ahead and try to put in the 8 pairs. So the first pair bonds this nitrogen oxygen, second pair here, and then 3, 4, 5, 6, 7, 8. And notice what I did here is I tended to put the pairs of electrons in the terminal atoms before I put it in the central atom. And usually that's generally a good practice. Okay, so we can hopefully see that here we don't really have a good Lewis structure because although the oxygens have octets, this nitrogen does not. It has 4 electrons. So what we're going to do is move this pair into the bond between this nitrogen and oxygen, and this pair into the bond between this nitrogen and oxygen. So you have nitrogen, and so there are 2 pairs here. There's oxygen here, like that. And so we have nitrogen here, and 2 pairs with oxygen here. And so we have a pair here for this oxygen and a pair there. And so this should be, it looks to me, a good, reasonably good Lewis structure. And the reason is, you can see at the oxygen here has an octet of electrons. The oxygen here has an octet of electrons. And then the nitrogen here also has an octet of electrons. You can see that these shared pairs count in the electron count for nitrogen. So what would be the structure? So in the end, you have nitrogen, and there's a double bond to 1 oxygen atom. And then there's a double bond to another oxygen atom. And then what you do is you have to indicate in this molecule that it has a positive charge. And so to do that, what we have to do is put brackets around the molecule, and then outside the brackets indicate that it has a positive charge like that. So this is the complete Lewis structure of a cation. So here it is the cation, the molecule, and then again what we have to do is put it in brackets with a positive charge. If it was an anion, in other words, it has a negative charge, you put the molecule in brackets and then put a negative charge. And we'll probably do that, some practice in class about that one. Okay, so now we're going to move on. So there are molecules where you can write good Lewis structures, but not all the atoms may have an octet, meaning that maybe you have some atoms that have less than an octet, or maybe you have some atoms that have more than an octet. And so you need to be knowledgeable as to when you can write Lewis structures where you have atoms that either have less than an octet or more than an octet. So let me give you a few examples of those. So a good example to start with is where we have a molecule that actually has an odd number of valence electrons. So all the examples we've seen so far is all molecules have had even numbers of valence electrons, and so we had pairs that we can move around. Now, not all molecules will have that situation. Some of them will have an odd number of electrons. So what do you do about that? So the first one we're going to consider is a molecule called nitric oxide. And so let's go ahead and write the skeletal structure for that. Okay. No. Okay. So let's go ahead and count valence electrons. So we have nitrogen, which has 5 valence electrons. And then we have oxygen, which has 6 valence electrons. And so what you can see here is we have a total of 11 valence electrons. So you can see we do not have an even number of valence electrons. So what do you do? Okay, so the way I think about this to start is I think about this, we have 5 pairs plus 1 extra electron. So let's go ahead and throw in the 5 pairs and see what happens. Okay, so the pair 1 here, 2, 3, 4, 5. Okay, so remembering we have an extra electron that we have to place in, let's go ahead and see if we can create octets. And so what you can see right now that neither the nitrogen or an oxygen atom has an octet, right? So what we can do is we can go ahead and move electrons in. So for example, you could move in this pair here in between the nitrogen and oxygen, and you can move this pair here in between the nitrogen and oxygen. And what would you get? So we would get something like this. And so we've moved in 2 extra pairs between the nitrogen and oxygen. So now it has a total of 3 pairs here. And here's the oxygen atom and with its pair. And you say, oh, great. All these atoms have octets. You're done. Well, here's the problem. You have 1 extra electron. And so you can see that if you put the 1 extra electron around nitrogen, it won't have 8 electrons. It'll have 9 electrons. If you put the extra electron on oxygen, it won't have 8 electrons. It'll have 9 electrons. So we can't use this. And so we have to think of a different approach. Okay. So here, let me just draw out again what we had before I started moving in electrons, and think about something else we can do. So how about this? Let me just move in 1 pair from, say, the nitrogen here, and then let's look at that structure. And not all atoms will have an octet, but that's okay. Some atoms, if they have an odd number of electrons, they don't have to have an octet. They can have 7 electrons and they'll be fine. So here, what I'm going to do is write out this structure here. And so we have this pair goes into between the atoms here. And so what you can see is this is what it looks like so far. And so the oxygen has an octet, but the nitrogen does not. But what we can do is put 1 more electron on that nitrogen. So now the nitrogen now has 7 electrons. And so that isn't the most stable structure in the world, but it's better than having 6 electrons. And so this is actually a correct Lewis structure. Now you can go the other way if you wanted to. You didn't necessarily have to put nitrogen's pair in between the nitrogen and oxygen. You could put an oxygen's pair between the nitrogen and the oxygen. So it would look like this really quick. See if I can do this right. Okay. I think it would look like that, yeah. And so here the odd electron would go around oxygen. So is there one structure that predominates? And the answer is yes, for reasons I don't quite understand. You have to take physical chemistry to understand this. But basically, if you have an odd electron, it prefers to be on a less electronegative atom. So this is the preferred structure. Okay, so let's move on to another one. One that may be more important, although you definitely need to know the one I just did. Okay, so how about boron trihydride? Let's draw a Lewis structure for that with the rules that we know so far. Okay, so boron's going to be in the middle, hydrogen on the outside, so that's fine. So boron here has 3 valence electrons, and hydrogen each has 1 valence electron. And so there are 3 of them there for a total of 3 valence electrons from the hydrogen. So you have 6 electrons total, or 3 pairs. Okay, so we connect here of the first pair, we connect boron to hydrogen. The second pair between this boron and this hydrogen, and the third pair here. So we've done with our valence electrons. We only had 6 electrons that we could use, 3 pairs. So we're done. So with the hydrogens here, they're stable, but how about the boron? And you say with the boron, well, wait a minute, the boron doesn't have an octet. Isn't that a problem? And the answer is boron doesn't necessarily have to have an octet. Sometimes it does, but most of the time it does not. Boron is in group 3, and group 3 elements do not have to have an octet to be stable. They can have just 6 electrons to be stable. So let me just kind of point that out in the periodic table here really quickly. And so I'll just draw this really fast just to point out when you have elements in group 3 here, boron, aluminum, gallium, and just so on. So these elements don't need octet. And so they don't need an octet, and they'll be happy with 6 electrons. So I'll just indicate that there. So that's just something to keep in mind when you draw structures. Okay, so let me turn it back. So to complete this Lewis structure, it'll be boron, hydrogen, hydrogen, hydrogen. So that is a good Lewis structure for boron trihydride. So let's move on. So the next one is beryllium dihydride. So we have beryllium dihydride. Okay, so beryllium has 2 valence electrons. Hydrogen has 1, but there are 2 of them. So there's 2 valence electrons, so you have 4 electrons here. So you have 2 pairs that you can deal with in the structure. So we put beryllium in the middle, better pen, beryllium in the middle, and then hydrogens on the end like that. So we have a pair here and a pair here. And so this is all the electrons we're allowed to have in the structure because we counted up a total of 4 valence electrons, or 2 pairs. So this is it. All we can do is put in 4 electrons. And you say, oh wait, so the hydrogens are stable, but the beryllium, we have a problem with beryllium. Okay, no, we probably don't have a problem with beryllium. And the reason is beryllium is an atom in the group 2 column. And if you have atoms in group 2, then those atoms are stable with a number of electrons that's less than an octet. And so in this case, beryllium will be stable with 4 electrons. So this is a stable structure. So let me just kind of point that out in the periodic table here. So here, beryllium, magnesium, calcium, those are elements in group 2. And so if you have those elements in a Lewis structure, they don't need an octet. So same rule here, they don't need an octet. They will be happy with 4 electrons in their Lewis structure. So that's just something to keep in mind. Okay, so we're going to go back here. Let me complete the Lewis structure really quick. So you put lines for the shared pairs, and that should be a good Lewis structure for beryllium dihydride. Okay, so moving on. Let me go back here. There we go. All right, 2 more, yay, and then we're done. Okay, So the next molecule is arsenic. And this is a nasty one. So this is arsenic pentabromide. Don't want to breathe that in. That would most certainly kill you. Okay. So what is the valence electron count for this molecule? So arsenic has, you can look it up, it's in group 15, or group 5, depending on the naming system you use. So it has 5 valence electrons. Bromine has 7 valence electrons, and there are 5 of them here. So if that's the case, we have a total of 35 valence electrons contributed by bromine, 5 from arsenic. So there's a total of 40 electrons, and then there are going to be 20 pairs. So that's a lot of electrons. So arsenic has the slightly lesser electronegativity, so it's going to be in the middle. So let's distribute the bromines around. So it is possible with elements that are in period 3 or higher, like period 4 and period 5, that those elements will be stable with a number of electrons that's greater than an octet. So you might have the central atom being in period 3 or period 4, and it will be stable, say, with 10 electrons or 12 electrons. And so this is the case with arsenic. Arsenic, as I recall, is in period 4. If it's in period 3 or 4 or 5, anything that's not period 2, period 3, 4, or 5, that atom will be stable with more than an octet of electrons. And so, as you can see, we're going to have to do that to bond all these bromines in the structure. So let me put in the 20 pairs. So I'm just going to quickly draw lines for the shared pair, 2, 3, 4, 5, and then we have 15 pairs left, 6, 7, 8, 9, 10, 11, 12, 13, 14, let's see, 15, 16, 17, 18, 19, 20. So this is a good Lewis structure for arsenic pentabromide. So again, arsenic, you can see that has more than an octet. It has 10 electrons, and that's permitted. So let me kind of explain that on the periodic table again. So just a note, if you have elements in the second period here, if you have carbon, nitrogen, oxygen, fluorine, or neon, these elements in the second period are required to have an octet to be stable. If you have elements, say, in the third period or the fourth period or anything lower than that, so going down here, those elements, they can have an octet, but they don't necessarily have to have an octet. They can have more than an octet. They can have 10 electrons or 12 electrons. So here is the position of arsenic, and you can see it's in period 4. So arsenic, because it's in period 4, it's not in period 2, it's in period 4, it can have more than an octet. So it did in that structure. Okay, so let's do the final one. The final one is selenium hexachloride. It sounds like another deadly molecule. Okay, so selenium hexachloride. Okay, so selenium, it's in group 6 or 16, depending on the system that you use to give you group numbers. So selenium has 6 valence electrons, and chlorine has 7. And then there are 6 chlorine atoms for a total of 42 electrons, valence electrons contributed by the 7 chlorines. So it looks like we have a total of what? 48 electrons or 24 pairs. Okay. So selenium, as I recall, is in period 4. So it can have a greater number of electrons than an octet to make it stable. It can have 10 electrons or even 12 electrons. Looks like it's going to have 12 electrons because we're going to have to bond 6 chlorines to it. And so let's go ahead and put in the electrons. There's 24 pairs. First pair, second pair, third pair, fourth pair, fifth pair, sixth pair. Now we put the other lone other pairs as lone pairs around the chlorine. So that's 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24. And so this is a perfectly good Lewis structure for this molecule. Again, selenium, it doesn't necessarily have to have an octet because it's not in period 2. It's in period 4, so it can have more than an octet. It can have 10 electrons or 12 electrons. Here, it looks like it has 12 electrons. Chlorines, though, do have octets and so should be stable. So this should be a good structure for the molecule. Thank you for listening to that. We'll see you next time.